So let's just see a theorem which is related with the properties of the length of the tangents, or with the properties of the tangents which are drawn from an external point on the circle. So let us suppose the theorem says that the lengths of the tangents drawn from an external point to a circle are equal. So actually we have to show this that if we are drawing any two particular tangents from an external point to a circle, then their lengths are actually equal to each other. So let us suppose if I'm just taking a figure in this particular manner, in which I'm just taking a circle with the center O and a particular external point P, and from that particular external point P, I am just taking the two lengths of tangents as nothing but PQ and PR. So let's just start the proof of this particular theorem. So first of all, I am just taking a given condition, that what is given to us. So a circle with the center O, a circle with a center O, and an external point P with PQ and PR being the tangents to the circle. And I also did the construction already in this particular figure. So my construction was like, I have just joined this particular center O with this Q and O with this R. So this is actually my construction. So the construction is join OQ and OR. This is my construction which I already did in this particular figure. Now let's just move on further towards the two proof condition. What we just wanted to prove over here, we just wanted to prove that this PQ is actually equal to this PR, that the length of the two tangents are actually equal to each other. So we just wanted to prove this length is equal to this length. Now let's just move on further towards the proof. So the proof of this particular theorem would be like starting from the very first condition. Since we have actually joined this OQ together and this OR together, so we know about this OQ and OR from the theorem number 1, that whenever we have any particular tangent which is drawn at any point of the circle, then it is always perpendicular to the radius through the point of contact. This information we already know from the theorem number 1 that we already did before. So starting from that particular concept, I'm just writing it over here, that the angle Q or the angle OQP and the angle ORP is actually nothing but is equal to 90 degree. So let us suppose if I'm just writing it over here, since the angle OQP is actually equal to the angle ORP, which is nothing but is equal to 90 degree from the theorem. Using the theorem, let us suppose if I'm writing it over here, using the theorem, what is that theorem? The tangent drawn at any point to a circle is perpendicular with or to the radius of the circle through the point of contact. So from this particular theorem, we know about this particular fact that with the radius, this particular tangent is actually making an angle of 90 degree. So let us suppose if I'm just writing it over here, this is my 90 angle and this is again a 90 degree angle. This is again a 90 degree angle over here. So this is 90 and this is 90. Now let's just move on further with these two triangles. As you can see over here, there are two triangles, that is the OQP and ORP. Now let's just move on further with these two triangles. So let us suppose if I'm just moving from here only. So let us suppose we are just talking about in a triangle OQP and a triangle ORP, and triangle ORP. First of all, we know that OQ is actually is equal to the OR. Why so? Because they are nothing but the radii of the circle. Since they are the radius of the circle, so they would be equal to each other. Now further, what we can say about the other side, that OP is actually is equal to OP. OP is actually is equal to OP, and furthermore we know that if this particular angle is 90 degree, then it is definitely a right angle triangle. This is definitely a right angle triangle. So hence, if it is a right angle triangle, then their OQ sides are equal to each other, or we can say OQ is equal to OR, and this OP side is already equal to each other because OP is common, because OP side is common. So what can we say about these two particular triangles? That they are congruent to each other by RHS congruency criteria. By RHS congruency criteria, we can say that these two particular triangles are actually congruent to each other. So let us suppose, if I am just writing it over here, that the triangle OQP is congruent to triangle ORP by RHS congruency criteria. So it implies that if these two triangles are congruent to each other, then by CPCT, we can say that this QP is equal to RP. By CPCT, we can say about this fact that QP is nothing but is equal to RP. So we just wanted to prove that PQ is equal to PR. So it means that we already are done with the proving concept that this PQ is nothing but is equal to PR. We can say from this particular fact. So hence it implies that the length of the tangents which are drawn from any particular external point to the circle. So let us suppose if I just write it over here, hence proved. This is what we wanted to prove in this theorem. So hence we have proved that the length of the tangents drawn from an external point to a circle are always equal. So remember this particular fact, because this would definitely help us to solve many problems later on. So this is all about the theorem number 2.